Okay. So I'm going to start with a polynomial function, let's say f of x equals x to the fourth minus 2x squared and plus 3. We are asked to find everything possible, anything that we can think of, and I'll show you what we think of in a minute. So I highly recommend get used to this table. You can invent your own. You can modify this one. You can use somebody else's. That doesn't matter, but you have to use a way of summarizing the information in a table. If you don't like this one, I'm fine. I'm not going to be hurt. My feelings are not going to be hurt, but you have to invent your own, modify this one, or create another, or learn one from somebody else. Okay, so notice that x is the variable in the problem. I have f prime and f double prime, and the function is squeezed between those two. If you want a different order, choose a different order. Do whatever you want, but you must summarize all the information somehow. I will definitely start with a domain. I have to. I have no choice. So it's a polynomial function. Domain, obviously, all real numbers. My next step is to plug in 0, because that will be the y-intercept, 0, 0. That will be 3. And I need to determine the end behavior, where the function is going. You can say you determine the x-intercept right, the y-intercept right away. What about the x-intercept? Yes, we can find the x-intercept as well. They're important, but since I'm not going to graph, I don't want all the details at this point. I just want us to get used to creating this table, filling it in, and make sure that these 3 rows work well together. That's my target for the next few minutes. Okay, the end behavior, very easy. Limit as x approaches infinity from x to the fourth minus 2x squared plus 3. And then limit as x approaches negative infinity from x to the fourth minus 2x squared plus 3. Can anyone give us, my hope is that at least some of you are watching and paying attention. So can anyone give us these 2 limits?
They both approach infinity.
Very good, because when it comes to infinity, these 2 don't mean anything. And when x approaches infinity, x to the fourth will definitely approach infinity, and negative infinity to the fourth will also approach infinity. Very good. Awesome. Thank you very much. Okay. So what I would normally do next is the x-intercept. I will find 4 solutions, but potentially not all of them real, but that's okay. So I can do that right away. This calculator has the option. I never checked with this calculator because I have my other one. So, but apparently there is what it's called polynomial. I don't know what SMLT2, but if you have this calculator, press 9 and press polynomial. So we want to, it's a cubic polynomial, press 3. And then I want to press next. And I will enter these coefficients. Oh!
Can you repeat that one more time?
Yes. So go to applications. And then at the top is polynomial. You have to choose. So you go to applications, choose 9. But if you have this calculator that I wrapped in plastic, because as you know, I spilled water on it, they're not as strong as the old ones at all. At all. You can drive over them with a tank and they will not crash, but these are not as. Anyway, so number 9, and then polynomial, because we want a solution. The degree is 4, and go to next, and the coefficients are a to the 4, so that's 1. Yes, that's correct. And then 0 for power 3, -2 for power 1 or degree 1, degree 2, and then 0 for degree 1, and then 3 for the free term, and then click on solve, and it gives us 4 solutions. But as you see, the second one has an I. The third one, as expected, is the complex conjugate of this one. So there are only 2 real solutions. So when I solve f of x equals 0, I get 4 solutions, but 2 are imaginary, so I will not even bother to copy them. So x equals -3.5 and x equals -0.88. So this is what we would normally do. And I would put them in, -3.5 and -0.88. Depending on what I get, I may have to redo my chart, because if what I find will be between -0.88 and 0, then I don't have enough room. So I have to rearrange my numbers. But that's okay. Well, I can do that very quickly. At this point,
whenever I put those values into my calculator, I get very different solutions.
let me check with my old calculator. I know I shouldn't say that I don't trust the new one, but I'm going to do 1, 0, -2, 0, and 3. It's thinking, and it's thinking. Come on. It's still thinking. See, that's the new calculator. Thank you so much for checking this. They appear from this calculator, they appear that there are no real solutions. I would have found the problem right away, but I'm so glad that you did. I'm doing it again just for the sake of the argument. So 0, yes. A to the third, yes. -2, yes. 0, yes. 3, yes. Okay, do it again. But what do you think is wrong with the other calculator?
I don't know, but I got all.
Yeah, -1. So they appear to be all real or imaginary solutions.
Mm-hmm.
Yes, I see that with my other calculator. I get the same thing. Yep. Very good. I would have run into difficulties and said, whoops, and I would have gone back to the drawing board. Yep. I have no idea. So now you see why I put parentheses everywhere. Now you see why I don't trust all the steps. Thank you. Thank you, Ted. I really appreciate it. You saved me. Good. Apparently there are no X-intercepts. So I'm going to say they're all imaginary. I checked twice. I have no idea why this one gave that. I will check later. I don't want to waste your time. That's not important. I'm glad we found the mistake early. That's the most important part. Okay, so this is gone. Did you have the exact calculator? Did you use the same feature?
I have the TI-84 plus CE, and I still got no real solutions.
Which means that I probably punched in something incorrectly then. Okay, very good. There is nothing else I can find about the function from the function itself. That is done. I have to move on to the first derivative, and I have to find critical numbers. I know that critical numbers will not come from f prime being undefined. It's a polynomial function. So f prime of x equals 4x to the third minus 4x. And when I set this equal to 0, of course I will divide by 4. I'm all about simplifying. And it's not being lazy. It's really simplifying the equation. So we get x here. Oh, okay. Let's go. Okay. So x cubed minus x equals 0. I factor out x, and then I have x squared minus 1. And then x and x plus 1, x minus 1. So there are three options. X equals 0, x equals -1, and x equals 1. These are all critical numbers. I go back to the table and put them in. Where do I put them in? Correctly, 0 here, -1, 0 here, 1, 0 here. At the next step, I will study the sign of the derivative. See what the sign of the derivative is to the left of -1, between these two, and 1 to infinity. The easiest thing to do is go back to the first derivative. This is what I would do, but you're free to do whatever you think is best. This is the derivative with 4x outside and x squared minus 1, which is x plus 1, x minus 1. And here's how I will continue with, we can study the sign as we did in the past with a table, or say, here's another way, -2, negative, 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 -2, negative, negative, 3 negatives. -0.5, positive, negative, negative. 0.5, positive, positive, negative. 10, all positive. At this point, and now immediately I have to determine these values. So I go back to the function. Where is my function? Right here. And I plug in 1 or -1. I know that this is symmetric. How do I know? See, x squared and x to the 4th, if I replace x by -x, it will not make any difference. So it's an even function because f of -x equals f of x. I'm hoping you remember this from pre-calculus. If I need to elaborate, you let me know. So if I plug in 1 or -1 in the function, it doesn't matter. So 1 minus 2 is -1. -1 plus 3 is 2. At this point, this is the moment of truth. For now, if this row does not work well with this row, then I'll say, oops, and go back to the drawing board. So let's see what we have. The function from positive infinity to 2 is decreasing, and that is exactly supported by the sign of the first derivative. From 2 to 3, yes, it goes up, and this is correct. From 3 to 2, yes, it goes down, and the sign is appropriate. And from 2 to infinity, it goes up, and yes, the sign of the derivative is appropriate for an increasing. So these two are carved in stone now. They're working well together. Okay, I exhausted everything about the first derivative. What did I do? I know the intervals of increasing, and I know the max min, and I will write them right this moment. -1, 2, obviously, is this situation. So negative, and then 0 or undefined, and then positive. So -1, 2 must be a local min. This must be a local max. This must be a local min. So I learned everything that I could from the derivative. Increasing, decreasing, max min. Now I'm moving on to the second derivative. So here's the first derivative. Not this, not this. No, of course, this. So when I find the second derivative, I will get 12 x squared and minus 4. I will set this equal to 0. And I get two solutions because I have 12x squared equals 4 or x squared equals 1 over 3 Ugly, but that's what it is. X equals plus or minus the square root of 1/3. At least I don't have to redo my table. So plus or minus the square root of 1/3. Negative the square root of 1/3. The square root of 1/3. And here is 0. And here is 0. I have to find the values of y, or f of x, for these two. I only need one. It's an even function. So when I plug in 1/3 in this function, I meant to write the square root of 1/3, of course. When I plug this in, I have 1/3 squared, which is 1/9, and minus 2/3 and plus 3. The least common denominator is 9. This needs a 3 and this needs a 9. So 1 minus 6 and plus 27. 28 minus 6 is 22/9. 22/9. 22/9. So final step, I have to study the sign of the second derivative. If it changes sign, this point becomes an IP, inflection point. If it changes sign, this point becomes another inflection point. If it does not change sign, no inflection points. Okay, so this is the expression for the second derivative. When I plug in 0, which is right here between solutions, I get a negative number. And it's guaranteed because it's quadratic, but let's say I plug in 10, it's going to be positive. I plug in negative 10, it's going to be positive. So we know that on this territory, the function holds water, as well as here, between this and this, and between this and this. And here it does not hold water, concave downward. Guaranteed this to be an IP, and this to be another IP, inflection point. So let's summarize a little bit, because I'm going to show you something, but I want to make sure that you understand what I just did. So, okay, so coming back here, what did I accomplish? I found the sign of the second derivative, so I know the concavity opening upwards or downwards. And I found the inflection points because the second derivative is 0 and it changes sign at that point. So notice what we just did. We determined everything about the function, x and y intercepts. There were no x-intercepts. There was a y-intercept, and we found the limits at infinity, the end behavior. We determined the first derivative. We found the critical numbers, and then we studied the sign of the first derivative. There is something called the second derivative test. The second derivative test, which I'm going to write in a minute. So coming back to our table, do not change anything because I will put them back in. I will make some corrections. Don't change anything. I'm trying to illustrate the second derivative test that I personally never use. But you may like it. I have to present it to you. Okay, so notice what I did. And I'll tell you why I don't use it. So I determined the first derivative. I found the critical numbers, but I did not study the sign of the first derivative. I said I'll do it later. And I'll show you how we do it later. So I went directly to the second derivative. I found the second derivative. I found where the second derivative is 0. And I studied the sign of the second derivative. I have to. So I know the function opens up, concave down, concave up. Now, can I go back and fill in the sign of the first derivative? Yes, I can. And here is how I do it. if I need a prop. Where the second derivative is positive, I know the function opens up. If in that interval where the function opens up, if there is a critical number, like in this case, what kind of point is negative 1, 2? This tells us that the function opens upward, and in this territory where it is opening upward, there is a critical number. What type of critical number could this be? Negative 1, 2. What type of max min?
Be a local max or local min?
It has to be a local min. It cannot be anything else if it opens up. The function on this territory between negative infinity and this point opens up. There is no opening down. It opens up because it opens up, and there is a critical number there at negative 1. The derivative is 0. Negative 1, 2 must be a local minimum. If it is a local minimum, then I know the sign. I don't have to study the sign. I can fill it in now. Now in the middle. And that is the second derivative test. Now in the middle, I know that the function opens downward. And in this interval between these 2 points where it opens down, it has a critical number. What type of critical number or what type of max or min will this be? 0, 3, if it opens down, for sure.
Local max.
Local max. So then I can fill in. This is sign of the first derivative. And finally, on this interval, the function again opens upward, and it has a critical number. What type of max min will this be? Will it be a max or a min? The function opens the local min. So at this point, I can fill in the sign of the first derivative that I was lazy and I didn't want to. No. So the point I'm making is use the second derivative test if you want. I'm going to write it as a summary for you to have it in writing. The reason why, if you ask me why I don't use it, I never do. Just to check, I use it to check, but I don't use it to determine the sign of the first derivative. I don't. Here's why. If it happens that I make a mistake on the first derivative, the mistake will carry over to the second derivative. I can't have that. I have to have control over the table. If these 2 rows don't work well, then I have to go back and look at my calculations. By the time I get to the second derivative, it may be so late that I won't even be able to find my mistake. I will probably have to start from scratch. So that's the reason why I never, ever